How are you doing this morning? Okay, I'm gonna need a little bit more, like, yes! Good morning! Okay, cool. My name is Raquel Vélez, as John so eloquently told you a little bit about me. So yes, I am a former roboticist, and now I'm a web developer. I am a senior software engineer at NPM Inc. We can talk about Node and packages and Node packages anytime you like, but today we're going to talk about math. Okay, so on a scale of to woo, how do you feel about math? Come on, I need some thumbs. Come on, come on. Yeah. All right, so I understand. Some of you are like, math. But let's face the facts. Math is everywhere. It is really, genuinely everywhere. Fortunately, for most of us as web developers, math is abstracted out, so we don't actually have to worry about it. We don't have to care about it as much as like the real pure diehards, right? And fair enough. But my goal for today is to kind of convince you, hopefully, that if you were to play around with the math, if you were to kind of go a little bit more hardcore with the math, that you might encounter opportunities that you never expected. And that could be really fun, really cool, and could be, a little mind-blowing. So, to get started, I have created a little project. Because I firmly believe that math education is backwards. I think that this whole notion of let's learn our addition and our subtraction and our multiplication and all that stuff before actually getting any context is kind of ridiculous. And that instead, I'd much rather start with context and then work our way backwards so that we know why we're learning the math. So, here's our situation. We have what is called a serial manipulator. Okay, it doesn't look like much because it's in 2D, but we're going to do this in Canvas in HTML5. And to kind of give you an idea of what a classic serial manipulator is, kind of think of your arm. So I'll do it this way. Okay, so this is your arm, right? Your arm is a classic serial manipulator. So just think of that, right? To give you a little bit more context, this is what you could do with it, right? Like, your legs are classic serial manipulators. Your fingers are classic serial manipulators. You could hypothetically use this stuff that we're going to talk about to build a little character in a game or something else. Use your imagination, have fun. But this is more complicated than we really need, so let's just focus on the simple stuff. Okay, so here is our environment. We have a canvas, like I said. We'll be using HTML5. Great. And then our manipulator has a couple of joints, right? Like our shoulder and our elbow, and an end effector, which is just kind of like, think of it as like the claw, your hand, whatever. Fancy robot speak, end effector. And then we connect these joints and stuff with links, right? And these links can be of any length. I use variables because I'm mathy, but if you want to assign that like 100 pixels, that's fine. Whatever, math. Okay. So that's it. That's our basic little situation. That's where we're going to try to build today. And let's get to some theory. Brace yourselves. This is going to be awesome, but it's going to be a little... I forgot to pick up the Mentos so I could like throw it at you. Stay awake. But stay awake. It's going to be cool. Okay. So we have a global coordinate system. All right. How many of you have played with Canvas before? Okay, awesome. Okay, so you know that basically, you have this global coordinate system in your canvas, and you have your x coordinates that go along the x-axis in that direction, and you have your y coordinates that go along your y-axis in this direction, right? And then if you have a point in space, you basically give it a coordinate of x comma y, right? This kind of makes sense. Cool. So these are defined in the global coordinate system. Mathematically, the way that we say this is we have this vector where we have our x and our y, and we do technically have a z, but because we're in 2D space, we're going to ignore it. It will be useful for those of you who are curious. Your z-axis kind of follows the right-hand rule. So this is z, this is x, this is y. And since we have x going this way and y going this way, then our z goes kind of into the wall. Those of you who've played with z-index before, you know that when you increase z, you go on top. So technically the z-axis is coming out this way, but the web has it backwards. We're going to ignore that. Fortunately, we're only doing 2D, so who cares? Okay. What this means is that when we're drawing our robot on our serial manipulator in our canvas, it basically says that we have global coordinates for all of our points and la-di-da, fancy. Cool. Another thing to keep in mind is that every joint has its own local coordinate system. The cool thing about math is that we get to say wherever we want our coordinate system to be. So by convention, we say that each joint has its own coordinate system. And also by convention, we say that the x-axis of each of those local coordinate systems goes from one joint to the next. What this means is, the beauty of this, is that now instead of having some, fancy x, y sort of thing, we can just say that our x coordinate for the next point over is the length of that link, and then there's no y. What this means, ultimately, is that our math gets really nice and clean and easy. And all because we're using conventions and fun stuff like that. Keep in mind also that your local coordinate system goes with the joint as it rotates. So this just means that the math continues to be easy even as you're moving things around. Am I making sense so far? Yes, good, okay. I need feedback. I don't do well without feedback. This is why I went to the web instead of robots. I can always refresh. Okay. So, let's talk about rotating around a joint. So when you rotate around a joint, you have some angle of rotation. We're going to call it theta because that's how the math people do it. If you wanted to call it bubblegum, cool, just be consistent. I don't care. But what that means is that as you rotate a joint, right, you have some before value of the next point after, and then an after value. And so how do we do that mathematically? What we do is we use a transformation matrix. In this particular case, it's a rotation matrix. And we say, okay, given this angle, this is how, if we apply this transformation to a vector, then we're going to get this new vector out. And this is what that looks like mathematically. So we're doing basically matrix multiplication. But for those of you who get scared of words like matrices and multiplication, just think of it as applying a transform to a point. So we have our before point, we apply this transformation, and then we have our after point. Cool? Cool. All right. We have two joints, so that means we have two angles, which means we're going to have two matrices, which also means that we've got 3 points, actually, because we have our end effector as well, and then 2 matrices, and it's like, okay, now I have to keep track of all of these random math things. But fortunately, we can simplify things a little bit. So to recap, we have a rotation matrix, and we have a point vector. And FYI, a vector is just a matrix, but just slimmed down a little bit. But then we have this great thing called a homogeneous matrix. And what happens here is we've actually combined the rotation matrix and the point vector into one matrix. This makes the math way easier because now instead of having to keep track of all these sorts of different things, we have one matrix for every single coordinate system that we care about. So you're probably looking at this and being like, oh my god, now you have these subscripts and superscripts, and how do I keep track of all these things? Well, okay, so basically what's happening here is I'm using some funky notation, I know that, but what I'm saying is that this is very specific to a specific coordinate system. And so I'm saying that if I'm going from joint 1 to joint 2, what does that look like? Well, that means that I have an angle of rotation, and I'm caring about what happens to this point here, right? So this is joint 1, joint 2. So what that means is, if I'm looking at from 1 to 2, I'm only working in the local coordinate system. So the angle of change that's happening in my coordinate system is just that theta 1. And then the distance, the point that I care about, is just like I said, that L1, just that length of the link in the x direction, and then y and z we don't care about because math. Math, yeah. Okay. Same thing happens if we go from the second joint to the end effector, right? And then there's also going to be another one from the global system to our initial joint, right? In that case, things are a little bit more complicated. I'm not going to show it because meh, why? But the whole point is that in this case, you know what your location is in the global coordinate space because we're not moving the location of this joint, even if we're changing the angle of it. Does that make sense? Okay. So we have this really cool stuff, but we have a tiny problem. We have this tiny problem in the sense that now we know where all of our joints are relative to one another, but we don't know where the joints are relative to the global space. Because ultimately, what do we care about? We want to draw these points on our canvas, right? So how do we take all of this local information and turn it into global information so I can say, draw my point at x comma y? Well, more transformations. Multiplication. Okay, so this is what happens. We take all of those local coordinate system homogeneous matrices and we multiply them together. So we're basically applying the transformation. For example, if we want to know the location of our end effector, right, in the global space, what we do is we take the transformation from our global system to our first joint, and then we apply the transformation from the first point to the second point onto that, and then we apply the transformation from the second point to the end effector onto that. And then what happens is we have this resulting matrix that tells us the transformation from the global system to our end effector. And very conveniently, because we're using homogeneous matrices, to get that location, we just grab this information right here. Boom! Nice and simple and easy and cool. A lot of you are like, this is not simple. This is not easy, oh my goodness. I've got you covered, don't worry. Okay. A lot of you who've played with Canvas before, you're like, okay, Raquel, this is really cute, but my brain hurts, and also, Canvas lets you do this kind of using its own API anyway. Okay, fine. Let's try using Canvas, and only Canvas. So, cool. Let's take a look at some software. So for HTML, like I said, it's just a really, really simple canvas. Looks like this. Got a little canvas tag, give it a little ID, get some width and height, great. But that's it. That's all we need for our HTML. Then comes the JavaScript. And in our JavaScript, we have this context. We have to grab it. And then we can start doing things with it, right? So no matter what we decide to do, we're going to have to draw a point. And so our point's going to look like this, right? So you have to begin a path, and then define the path, and then kind of fill it or whatever. And then to draw lines, because we're going to need our links, we're going to need to, again, begin this path, move from one point to another point, and then draw that. There's a lot of dancing in Canvas. But then there's also this API. There's more stuff to it, which is kind of cool. You can save and restore, which basically says, okay, if I have this configuration of my canvas in terms of like orientation and position, then I can call that back later, and this is going to be useful if we're just going to use Canvas. We need to clear our rectangle because we don't want to keep drawing stuff over and over again. And then this is kind of the key piece, right? We can rotate and we can translate. So let's go ahead and see what happens if we do this. All right, so now we're going to do a little bit of fun computer dance stuff. And hopefully, haha, excellent. Okay, so here I have a canvas, and I've built this really basic API. So like I said, we're drawing a point, right? So it's exactly like I said before. Drawing a line, same thing, clearing rectangle. And so let's see what that looks like. So if we draw a point at, say, 100, 100, and we make a little red dot, there it is. Really cool, simple. And then if I want to draw another point at 200 and make it yellow, should probably spell that right. There you go. And then I can draw a line as well. And that's just from the first point to the second point. I'm going to make it a blue line. Bam. And so that's just canvas. Cool. No big deal. But then let's clear this rectangle. Get rid of that. But now I can draw a manipulator. And so this is exactly the one that we were talking about, right? And then we can give it some angles, just so you can kind of see what I'm talking about. So I've given the first joint an angle of 10 degrees and the second joint an angle of 50 degrees. And that's what that looks like. And I can change that around. Boom. Wham. Yay, okay, so sound effects are good. But what does that draw manipulator function look like? So I have my important little bits and pieces here. But I want to call out this stuff. Can you see this highlighting? Yeah, okay, cool. So I'm going to do a little bit of a dance. So what happens is we clear this rectangle. We're going to save our orientation and position of our canvas because this is going to be important, otherwise things get really weird. And I'm going to draw my first point, right? And then I'm going to translate. I'm going to go walk over, and then I'm going to rotate my whole canvas, because really what we're doing is we're taking the canvas and we're moving things around. I'm going to rotate, I'm going to draw something, and I'm going to go all the way back to the beginning. And then I'm going to go back to the next spot, and then I'm going to draw, and then I'm going to rotate, and then I'm going to draw, and then I'm going to come all the way back. And then it's just this dance that constantly happens back and forth every single time you want to change things. So yeah, okay, so you avoided the math. Cool. But it's kind of annoying. Anyway, so just to kind of add a little bit of funness, I added this little joint slider system so you can actually see how things kind of look. And this is all on canvas, so that's cool, right? That's awesome. All right, fine. I will concede you could do this in canvas. Wait. But, yes, okay. So, okay, what's the lesson here? It's possible. It's totally possible. But I'm talking about math, and so we're going to do things the math way, because I said so. Hopefully I can convince you that it's worthwhile. So let's bring in some Node. How many of you have worked with Node before? Excellent. All right. Okay. So what I've done is I've created this module called Vector. And Vector is a robotics-focused linear algebra module that basically takes care of all of those homogeneous matrices and rotation matrices and vectors so that you can kind of play with all that stuff. And I know some of you are thinking, but Raquel, we're doing this on the front end, and Node is for the back end. Well, there's this wonderful module called Browserify that actually lets you it lets you take those back-end modules and put it on the front end. And I'll show you a little bit of that in a second. So it's pretty cool. Anyway, so this is what Vector looks like. We've got P and R and H, just like our point and our rotation matrix and our homogeneous matrices. I've defined some link lengths, and I've created an origin for the top of our robot. And this is going to be a little, whatever. Anyway, so this is what that looks like. So what I've done is I'm creating these homogeneous matrices, right? And I have my rotation matrices and my points, my vector, my little point vectors as well. And I'm applying these transformations. That's what the dot thing does. So this is like multiplying matrices for you. So you don't actually have to think about how the math works. You just have to know what to put into the math. And then, like I said, you can grab the locations of all of those joints in the global space just by doing this getPoint function. So cool. So let's do this with Vector in Canvas. More demos. We need some midway music. Okay. So next demo. So what I'd like to show you here is I have this vector, which Browserify, what it does is it basically gives you this, it defines require for you, and then it just throws everything into front-end code, which is pretty sweet. What that means is that then I can say require vector, just like I would in Node, but I can do it on the front end. And like I said, here's my calculating joints. And I'm still going to have to draw my point, and I'm still going to have to draw my line, just like before. But then I have a new draw manipulator function. And all right, so let's play with some sliders. So what's happening here is it works exactly the same way, right? Except now, instead of doing any sort of silly dancing, all I'm doing is I'm saying, calculate my joints for me, and then draw those points and lines. That's it. That's all that does. So now I'm letting the math take care of all of the actual like dancing bits and making it so that I can just draw. All I want to do is draw. So that's pretty cool, right? Cool. Yeah, okay, cool. I mean, you can tell me it's not cool, and I'll just kind of scowl at you, but, you know, you're allowed your opinion. I just want to hear it. Okay. So, back to here. Okay, so what did we learn? It's exactly the same result, right? So, yeah, okay, Canvas can do that, but so can the math. Cool. Let's talk about robots. This is a serial manipulator. This serial manipulator is, it's a KUKA robot. You may or may not be familiar with KUKA robots. They're the ones who build cars. They make actually the first time I saw one was at a Mercedes-Benz plant in Germany. So it's pretty sweet, right? It's got a claw, but the claw could be anything. It's like the end effector could really be anything. It could be a welder, it could be just a pick and place sort of thing, but it has joints and everything like that. See? Yeah? Look familiar? But what's cool about this one, just FYI, it's actually copying the Gutenberg Bible. So what it's doing is it's drawing the Gutenberg Bible, kind of, because, you know, that's useful. Anyway, so let's talk about kinematics. Robot kinematics is really simple. So kinematics, the word itself, just means the study of movement. So we're going to study robot movement. And there's two types of kinematics. The first one is called forward kinematics. And what's happening here is that we basically have a function, right? This is just like in regular JavaScript where we have a function and a couple of parameters. What happens is we put in the parameters of the angles, and out we get points. So in this case, this is what we've been doing the whole time, right? So we put in angles. We've got our angle 1 and our angle 2, and then out we get kind of our end, our global coordinates of our points. But then there's another version. Oh, I should also mention that forward kinematics only have a single solution, which is really convenient, right? Because no matter what your angle is, your end effector is going to be in one spot. May not necessarily be unique, but it will only have one solution, which is really useful. But then we have inverse kinematics, which does the opposite. In this case, we're putting in the location of our end effector, and we're getting out our angles of interest, right? So in that case, what that means is it's like putting your end effector in a certain spot and then trying to figure out, well, what do my angles need to be to get there? And what's interesting about that is that it's not a single solution, right? There's not a unique solution to that, because if my end effector is here, my angles could be like this, or they could be like this, or they could be like this. So it's a little bit harder of a problem. Kind of a fun way to think about forward versus inverse kinematics is forward kinematics is like you trying to grab something, like you know that you need to change your angles to go out and find something, whereas inverse kinematics is like walking. Like you're like, okay, I know that I need to put my foot here, so what angles do these need to be in order to move forward? Cool. For this, we use algebra. Eventually, with more, when I get around to it, I'm going to incorporate what's called the inverse Jacobian, which will allow you to have n number of joints and then be able to calculate the inverse Jacobian. But that's a lot of mathy words that you don't need to worry about if you don't like them. Okay. So let's do a demo with forward and inverse kinematics. Okay. And if you guys want to give me some, like, you know, transition music, I would love that. That'd be great. So what I'm going to do, actually, nope, just kidding. Keeping that on. Okay. And So I'm actually going to use this exact same thing here. But like I said, so this is forward kinematics, right? And I'm just changing the angles of each of the joints, and that's drawing everything out for me. But inverse kinematics is if I move this around. If I move this around, all right, you don't want to play nice, that's fine. But basically, you can see what's happening, right? It's saying, okay, I know where I want my end angle to be, and you'll see that it can kind of jump sometimes. So if I like change this around, and then if I decide to kind of, you see how it jumped? That's just because mathematically there's more than one solution, so it's just picking that one this time. But let's think about that. Can Canvas do that? Can Canvas determine all that stuff by itself using just its simple API? The answer is no. No, it cannot, because you'd have to implement some sort of mathematical reasoning in order to calculate what that inverse function looks like. So, so what's the lesson? We learned that Canvas can't do that. Hopefully I've convinced you a little bit about how cool math is. I don't know if you thought that was cool. Hopefully this next bit will be, though. All right. So now we're going to get to the really cool bits. Let's go beyond the browser. Let's leave the computer, well, let's leave the browser, except for like little bits. Let's go beyond. Okay. This is Manny. You can say hi to Manny here. I don't know what's going on, but little stickers not working quite the way I want it to, but that's okay. Anyway, Manny is a manipulator. I'm really clever with the names. You can build Manny at home. Manny is just some hardware. I'm using an Arduino Uno, a breadboard, some servos. I've got some sticks and a little platform, which is just this wonderful little can. It's really fun going through customs. Actually, they don't even care. But it's not a particularly expensive robot. It's just something you could build. You can build it at home, or you can build it at your next NodeBots event. And the great thing, so I'm going to use exactly the same code. Exactly the same code. The only thing I'm going to add, though, is this one module called Johnny5, which, if those of you who are familiar with jQuery, might appreciate Johnny5, because Johnny5 is like the jQuery of hardware. Incidentally, the guy who created Johnny5 is also on the board of jQuery. So how does that look like? Basically, the way it looks is you say, okay, I'm going to instantiate a servo. This pin is the pin that it attaches to the Arduino with. So the Arduino sends a little signal. It says, via pin number 9, I'm going to talk to this servo. And then you basically say servo.2, and you give it an angle. Pretty easy, right? There's more to it. We're going to skip it for now. I'm going to put all my code up so you can see what it looks like. But yeah. So, demo time. This should be fun. All right, because this is like the biggest demo, can I get a little bit of like music? Just a little. That's good. I'll do that. That's fine. Okay. So I'm actually gonna have to switch over to another sort of thing. What's happening here? Oh, you can't actually see that because I didn't do that. There. Okay. So I have this. I'm using Socket.io to be able to talk to the front and the back. Because it's hardware, I need some sockets or any sort of method to have everything talk to each other properly. But basically what's happening is I'm sending commands. I'm having the computer do all the calculations, and then I'm sending commands via USB cable to my little Arduino, which is hooked into all the servos with a breadboard to do all the fancy magic stuff. Using really technical terms here, I know. Okay, so hopefully, okay, hello, Manny. All right, so in the same way, we're doing forward kinematics. and moving individual things. And then I can also do, you'll notice that it's been inverted because Manny, hopefully you can, I know you can make the little transition in your head. But anyway, so then I can also do inverse kinematics. And Manny can say hi. And that's it. So, yay, Manny! I just like the way he waves. Like... All right, cool. So, that was awesome. Well done, Manny. You didn't leave me down. I also have a video if you want to see Manny in his element in wonderful sunny California. But you can basically just see how this is what I do in case things go wrong. This is my backyard. I've got roses. It's pretty cool. I don't know how to plant roses or do anything with it, but that's okay. So yes, you can see the inverse kinematics. And awesome. Cool. All right. So what's the lesson we learned here? Math works everywhere. Not only is math everywhere, but math works everywhere. This is completely, doesn't matter what browser you use, doesn't matter if you use Canvas or WebGL or whatever. Doesn't matter if you use sticks or iron pipes. Doesn't matter. It's math. The math part is everywhere, and it works everywhere. And it's completely language agnostic. You don't have to do it in JavaScript if you don't want to, but come on, you know you want to. The point is, maybe you don't need math everywhere. Maybe you don't need math in your day-to-day coding. But I really think that if you do try to understand why is there math, where is the math, how is the math, it might open your eyes to some cool opportunities. And yeah, so consider using math next time, or at least digging in, finding out what's going on, right? Like I said, dig in. But most importantly, have fun. If there's one thing I want to make sure everybody leaves here with, it's that if you're not having fun, you're not doing it right. Have fun. Go. Do cool stuff. Thank you very much. Appreciate it.